Okay, so what we'd like to do is essentially process updates and queries. So you can have a edge deletion, and then the dynamic algorithm should be able to process this edge deletion. You can have an edge insertion. The dynamic algorithm should be able to process this insertion. And at a certain time, the user can ask, say, pairwise a graph property. And in this specific example, it's just shortest path between two vertices in the underlying graph. And the user can ask, what is the shortest path distance between U and V? And you will have to answer. You'll have to give an answer, right? And this answer can be either exact or approximate, depending on what you're looking for. And there are two things that we really care about. One, obviously, is the approximation guarantee, how good your solution that you're putting is. And two other quantities that really care about is the update time. What is the time to handle this edge insertions and deletions? And the query time, what is the time to answer this query that the user is asking? Okay. So I hope the model is clear, and I want to make here just, I want to clarify something. So today I'm mainly going to look at graph properties, which I call like pairwise graph properties. And you can think of shortest path, like what is the distance between U and V, say effective resistance, max flow. And you've seen in previous talks, for example, David talked about matching, and Jan talked about dynamic matrix algebra. These are a bit different from what I'm going to talk about. Okay, so let's start with something that probably everybody has seen here. And this is the notion of graph sparsification. And the idea is, I would say, quite intuitive. You are given a dense graph. You would like to approximate it with a sparse graph, and you would like to preserve some graph property. Okay, as simple as this. So your graph is dense. You might want to make it sparse, but you want to preserve something. Okay. And what are some typical examples that we usually see? Well, back in the 90s, we have this notion of spanners, where you preserve shortest path distances. Then you have this notion of cut sparsifier by Benzer and Clark in '96. And this also this new, well, well, in the last 20 years, this is the notion of spectral sparsifier, which was introduced in this beautiful work of Spearman and Tang in the context of solving Laplacian systems. And what is the connection of these things to data structures or dynamic graphs? Well, these things have been used a lot, namely in the speeding up dynamic minimum spanning trees. For example, there are also recent work that dynamically maintain this cut and spectral sparsifier. But one drawback of all of these techniques is that whenever you're trying to solve a graph problem and just maintain a sparsifier, usually this would mean that whenever you want to query the Sparsifier is sparse, but it doesn't go beyond this linear barrier, right? Because if you replace m by n, essentially, and you run a query, I mean, you run a static algorithm on this part over here, then, I mean, this one and the Sparsifier there. So you're going to spend at least linear time. And the main question that I'm asking here is, can we go below this linear barrier? So I'm looking for sublinear algorithms in the number of nodes, okay? So I'm not happy with like n to the 1.5 or 4 or something like that. Okay. So today I'm going to try to introduce to you this notion of vertex sparsification. Instead, I think this is well less studied, at least in the literature. I don't, even within algorithms, I don't think many people know about it. So probably this is, at least you have the chance probably to learn something about it here. And I think it's very useful, as you will see. But it has been gaining momentum over the last years. So the idea is fairly simple. I'm given a graph. I have a set of vertices. Some of them are red and some of them are black. The red vertices are the vertices that I care about. And I would like to construct a Sparsifier that retains these red vertices. Okay, so it must contain this red vertices that I care about and preserve some graph property, say, I don't know, maximum flow, shortest path distance. But now, because this black vertices, you can get rid of them, essentially. You would like to preserve the property only among terminal vertices, only those that you care about, okay? So you're not trying to preserve shortest path among other vertices that you don't care about. You got rid of when you did sparsification. So you can think of this as deleting vertices or vertex reduction. Okay, and obviously what is the goal here? You would like to have a small approximation. So the quality of this Sparsifier should be as good as possible. And you would like that the size of the Sparsifier is as small as possible, right? You want to minimize these two quantities. Are there any questions about this definition? I mean, this is a bit high level, but I will get into the details of this. Yes? No, it can be anything. Okay, it's clear? So the question was whether age is required to be a subgraph of G. But I'm saying it's not required to be a subgraph of G. Okay? It can be anything. Okay? I will, yeah. In some So in some applications, it's required to be a minor, but I'm not going to talk about it today. Okay? A minor of the underlying graph. Okay, so what is the connection of data structures and vertex sparsification? So how I'd like to view this, it has been sort of implicitly studied, at least in the planar graph literature before we started doing this. At least if you go back to these classical papers on maintaining reachability information in dynamic planar graphs, or shortest paths, or bounded connectivity like 2-3 vertex or edge connectivity, maximum flow, you can see sort of this vertex sparsification going on. But the main question I would like to address in this talk is, what about general graphs? So can you use vertex sparsification to design dynamic graph algorithms? And here the goal is, instead of just trying to pick one problem and make progress on this, I'm trying to build theories, right? We are trying to say that there is a paradigm that if you have an efficient graph sparsification algorithm, then you can get dynamic algorithms. So this is the goal. I'm not going to talk much about the meta theorem, unfortunately, because I don't have time, but I'm going to try to tell you at least 2 applications of this, and mainly focus on effective resistances. And briefly towards the end, I'm going to talk about the dynamic max flow problem. Yes. Sorry, what are those? Okay, so usually it's going to be proportional to the number of terminals. And these terminals are the vertices that you care about. Okay, so ideally you would like to have T, where T, cardinality of T, where T is a terminal set, but it could be also larger, like poly T or something like that. And even for some application, poly T is enough, even very large polynomial. Okay. So that's what I plan to talk in the next few slides. So first, I'm going to tell you how to do vertex sparsification for effective resistances. Then I will actually tell you how to use this to solve dynamic systems, dynamic Laplacian systems, and effective resistances. And then I will get a bit into the technical details of this. And finally, I will tell you why you should care about this. Okay, so this is just not some artificial work that we are just doing in the dynamic setting, but this really has applications in algorithm design. Okay, so let me start with the notional Laplacian. How many of you have seen Laplacian before? Can you just write? Oh, well, it's pretty good. Okay, so there are many definitions. One way I would like to view it is as follows. So I give you a graph. You can view it as a resistor network. And then let's say I have voltages on the vertices. It's just an n-dimensional vector on the vertices. And I define the Laplacian to be the unique symmetric n by n matrix, such that the following quadratic form is, that realizes the following quadratic form. So there is also this very famous notion where you take the degree matrix, the adjacency matrix, and you subtract this from one another. Okay, so why are the Laplacians useful? When, at least from this electrical flow point of view, they appear in a natural way when you try to compute voltages when you route 1 unit of current in this resistor network from S to T. Okay, so if you want to compute the potentials or the voltages on the vertices, you solve the following Laplacian system that you see over there. Okay, and so now we start asking computational questions related to this object. We say, how fast can you solve the system? Well, you can do causal elimination to solve the system, and this takes n cubic time. So you repeatedly remove one vertex from the graph, and you recurse on the remaining. And then there is this beautiful work of Strassen, who did fast matrix multiplication. And that showed that you can solve the Laplacian system in better than to the cubic. And nowadays, I think the best constant, the best omega is until 2.37. And then finally, there is this breakthrough work of Spearman and Tang that showed that you can solve the Laplacian systems to high accuracy in near linear time. And this m is the number of non-zero entries in the Laplacian. Okay. Closely related notion to Laplacians is this notion of effective resistance. And one way of viewing it is the ST voltage difference induced in this network when you route one unit of current from S to T. You can also think of it as computing the pseudo-invertible Laplacian and then just looking at it for entries, as you see with the formula over there. And so why do we care about this? Well, this seems to be another way of defining metrics on graphs. So we know we are now used to actually defining distance or like measuring distance using L1 distance or shortest path distance. This is, you can think of this as L2 metric or another way of measuring distances of graphs. And it also has connections to random walks. For example, it's tightly connected to the commute time. And the commute time is basically saying that if you do a random walk from S to T, what is the expected time it takes you to get from S to T and back to S. Okay. So now we look at this natural problem. We are saying this underlying electrical network on the left is changing, is undergoing either edge updates or conductances are changing, resistances are changing. And we would like to maintain this effective resistance dynamically, okay? So be able to insert edges, delete edges, and query at any point of time. And what is the effective resistance? And again, you would like to obtain a small approximation and hopefully small update and query time. Okay, so let me try to convince you that actually lazy strategies don't work for this problem. And there are a couple of other graph properties that exhibit similar behavior. And the reason is as follows. So it seems that this effective resistance metric is very sensitive to small changes of the network. Okay, and why is this the case? Well, if you look at this example, I have this graph. It has two connected components as ST are disconnected. So if I add one edge, then obviously the effective resistance is going to be that one, because I have a path going from S to T of length roughly m-2/3. And then if I add another edge, it's not that bad because it just drops by a constant. If I add another edge, it just drops by a constant again. And you might think, okay, what about the strategy of I compute an effective resistance, and since it's changing just by a constant, maybe you know, I keep the solution for a bunch of updates and then I recompute from scratch. But it seems that after a constant number of updates, if you add an edge from S to T, then this drops to 1. Okay, and so it's very sensitive to updates. For example, you don't have this problem with unweighted max flow or unweighted global min cut or similar problems. Okay, so it's very sensitive to small perturbations in the graph. Okay, so let's review what we know about this problem. So there are some old algorithms, and probably now these have been improved by this work of Jan, Tachapon, and Danupon. But this is, if you want exact solutions, then you will get something, but mainly those are going to be superlinear update times. So if you want to maintain a special cut Sparsifier, it's known that you can. This one instead. Okay. Exactly. Or very sensitive to my voice, who knows? Okay, so the second one basically says, if you maintain a spectral vertex Sparsifier, you can always query in the Sparsifier. That's why you get this n update time. N query time. The update time is very fast. It's just polylog. And then we also proved some conditional lower bounds, saying like in general graphs, you can go beyond linear if you want exact. And even in planar graphs, if you want exact, you cannot go. Not actually, these are not. I think, yeah, okay. For planar graphs, actually, we got square root of n, and I will talk briefly about that. And in general graphs, we have a bunch of papers by now. I think one paper, the first paper that proved that you can do something sublinear, is this work by Durfee, Gao, myself, and Richard Peng. And there we show that you can do m to the 3/4 and m to the 3/4, depending on, and then m to the 5/6, depending on the graph sparsity that you're looking at. And even for general weighted, we have some follow-up work saying that we can push the running time down. So now, why is this surprising? Well, it was a bit surprising to me, at least, because, for example, for shortest paths, we can get such high accuracy algorithms. So shortest paths, all algorithms that we know kind of pay this spanner trade-off in the query time, update query time and the approximation trade-off, right? And it seems like for other metrics and graphs, you can do much better. And so you can get high accuracy approximation, all pair effective resistances, and you can get sublinear update times. So yeah, this is one surprising thing about effective resistances. Another one is that actually at this talk, all of these results that I mentioned, I think majority of them works only against oblivious adversaries, and I'm not going to get into the details of that, but I know that at this talk there is a work actually coming up with a general framework where they prove that this result can be made work against adaptive adversary, but at the cost of increasing running time to 3/4 plus little 1. Okay. Are there any questions about this type of results that you see over there, or? No? Okay, then I will continue. So in addition to this, we also expand this work to work with Laplacian solvers. So we have a definition of what is a dynamic Laplacian solver. So again, the underlying matrix is changing, but now instead of, because we know the solution vector can have up to n entries, and what we look instead is we want to have query access to a specific coordinate in the solution vector. And we want to make sure that this is a good solution with respect to the induced out norm. And again, we can extend these techniques and show that you can solve dynamic Laplacian systems in sublinear time. And previous works, as you saw from Jan's talk, were all based on some sort of doing a fast matrix multiplication or rectangular matrix multiplication, and then they couldn't go below this linear barrier. So the message here is that if you look at if you look at this subclass of linear systems, then you can get some linear times. Okay, at least this is what this is telling. Okay, so let's talk a bit about vertex sparsification. This slide, I think it might be a bit dense, but actually it's not hard at all. But throughout the talk, I will omit weights. So maybe this clique that you see over way is weighted. But let's look at the following algorithm. So let's assume for now I'm given this simple graph, which is just a star. Okay, I have one non-terminal vertex, this black vertex that you see in the star G, and I don't care about this one. I want to get rid of it. Okay, and the question is, what is the graph that you have to put on the neighborhood of this star so that you preserve all pair effective resistances, or you preserve all solutions to the Laplacian system with respect to the coordinates corresponding to the neighborhood. Okay, so this is the basic question you ask, and this is the question asked in physics, also is known as Cron reductions, and there are many actually definitions in the literature. And yeah, it turns out that there's a very fairly natural way, if you know a bit of electrical networks theory, there's a fairly natural way of putting weights on this clique. Unfortunately, as you see, even if you start with a tree, like this is just a tree, this star, right? The graph becomes very dense. Okay, and obviously this is not good because we want fast algorithms, like, and if you repeatedly do this, so if you take a big graph and then this graph will be, the vertices will be labeled, some will be labeled black, some red, and you repeatedly take a black vertex and put a clique on top, then you will get simply Gauss elimination on graphs, right? And the problem with this is that it's very inefficient. It can be as bad as cubic. It can be as bad as a cubic running time. And the good thing is that it's an exact Sparsifier. So you can show that the underlying Laplacian that you get after doing this elimination preserves everything exactly. Okay, you don't lose anything in approximation. So you have actually straight off again between the runtime and the approximation. Okay, so now this leads us to this notion, which is known in the literature as a spectral vertex Sparsifier. Okay, so what I would like to do now is have a sparse approximation of this clique structure that you get from these eliminations. Okay, which is natural, right? So I have this big graph that you see over there, and how can I get this small graph? There's a very easy two-round algorithm. What you do is you essentially do first Gauss elimination, then you do Speedman-Tank spectral Sparsifier on top of that. You can do that in 2 rounds. It's not that hard. But the issue with that is that still you are still paying this very big price in running time. Okay, so the running time is still cubic in the number of vertices, and ideally you would like to do this more directly. Okay, and then there was this work by King and Sachdeva, and this is also giving you the simplest Laplacian solver out there, which essentially says that instead of putting a clique on the neighborhood, you put some carefully chosen random graph, and also you do some random permutation on the illumination. And this ensures that you can compute in near linear time a high quality, I would say, spectral vertex Sparsifier, and the size is almost optimal up to some log factors, because this T is the number of terminals that you care about, and this epsilon square dependency, 1/epsilon square dependency, it's inherent in the spectral approximation guarantees. Okay? So now, when I saw this result, at some point when I was doing my PhD, I asked myself, okay, can you use this to do something with dynamic graphs? And the answer was yes, but I needed at that point planarity. Okay, so if you have a planar Laplacian, then it turns out that this is very useful. And you will see it next slide. And obviously the next question is, what about general Laplacian matrices? And I also am going to talk about that. Okay, so let's do first the easier case a bit. So probably those who have worked with dynamic, or not dynamic, even actually planar algorithms, they know one tool, very useful tool in planar algorithms is called arc division. So it's essentially, I give you a graph and I would like to partition the graph into a subset, into vertex sets with our edge disjoint, but they do share vertices, and they are called boundary vertices, such that the boundary of each such cluster that is induced by this partitioning is small. Okay, and by small, if the size of the cluster says R, then the boundary is square root of R. And this just follows from the planar separator theorem, which says that every planar graph, there is a separator of size square root of M. This is a classical result. So you just apply that result recursively, and then you get this partitioning of the graph into clusters with small boundary. And these boundary vertices you see are labeled as red vertices. These are called terminals in our terminology, okay? So boundary, this comes from, I think, differential equation. So, but okay, it doesn't really matter. So what you're doing now, the goal is very simple here. What we really want to do is actually construct sparse equivalents of these clusters only onto the boundary vertices. Okay, so we want to construct a graph because the boundary is small. We want to construct a graph only on the boundary. And this we will do using this King-Sachdeva spectral Sparsifier, vertex spectral Sparsifier. Okay, and so what happens now is that these graphs that I have over here are just lying on the boundary vertices. Okay. So whenever I delete an edge, let's look at edge deletions only for now. I think insertions are very similar. If I delete an edge, what I do, I go to the cluster that contains this edge, and then I just recompute from scratch. Okay. As simple as that. And if I get a query between S and T, then I kind of need to merge these Sparsifiers together. So here I'm using some notion of decomposability of these short complements or approximate short complements. And then once I combine these Sparsifiers together, because they lie only on the boundary, the size of the Sparsifiers is actually smaller, and that's why you get a speed up. So this is essentially the algorithm. Okay, it's just using the fact that you can get this cluster into small boundary. And we know that you can't have this for general graphs, but you can have it for, I don't know, planar graphs or minor 3. Graphs with special structure. Okay, and you can even, so this will give you n to the 2/3 runtime if you just do some very simple math and optimize the time and the query time. And you can actually improve this if you do a hierarchy of this. So essentially by hierarchy, I mean, you will recurse on this boundary vertices. You can think of it like that. Or doing nested dissection. Okay. So let's talk about the general graph part. So what do we do about general graph? Okay, so right now I've been talking about a lot of things, but if there is one slide in this talk they would like to remember, maybe it's this. And this seems to be useful, and it has been used, I think, in quite many papers. potentially including the current max flow paper in linear time. And this is the notion of just adding a terminal to this to the current Sparsifier. So I will spend some time here because I think it's important to understand. Let's start with this setting. I give you a graph. I give you a set of terminals T. And now, let's say you have computed already a short complement or an approximate short complement with respect to this terminal set T. So now the question I ask is, how efficiently can I declare a non-terminal vertex a terminal? Or how efficiently can I undo one of these eliminations? You can view it like that too, right? So you want to go back, essentially, one step back. Okay? And it turns out, if you know how to do this, then all edge insertions, deletions, queries, all reduce to this operation. Why? Because say I have two terminals. Sorry, I have an edge which has been updated or deleted. I take the endpoints of that edge, I declare them terminals, and then I work on the Sparsifier itself because it contains these edges, right? I update in the smaller graph. I don't have to work with a large graph. The same with queries. I have an SNT query. SNT don't seem to be in the Sparsifier. I just add them as terminals. If I can do this efficiently, then everything else becomes much easier. Okay, and this doesn't work only for L2 based things or L2 based distances. In this case, effects per day. It works for shortest path. It works for maximum flow. It works for cuts. Actually, it works for quite a few graph properties. But obviously, the definitions might be a bit different. And for cuts, you will see today, hopefully, what the definition looks like. Okay, so and this will heavily rely on this fact that. For example, all these properties share this additivity property. So for example, if you take a short complement of two graphs with respect to this terminal set, you can first compute the short complement of this graph on G and then leave the M aside. And this is fine, as long as they share this terminal set. Okay, so what we prove is the following. So in this paper, we prove that for L2 based distances, or for more generally for short complements, we can come up with an algorithm that supports this add terminal operation in M to the 3/4. We have other variants too, but I'm explaining here the simplest one. And you see also we have this dependency that the size of the terminal set must be at most M to the 3/4. If it exceeds that, then you just recompute from scratch. But then you can amortize the running time to the. So essentially, just having this gives you right away the effective resistances, like dynamic effective resistances. Okay, so does anyone have questions about this theorem? If not, then I will at least try to talk how we get this. So yeah, again, I think I would like to spend more time in this slide because I think this is useful. Any graph property you give me, if you know how to efficiently handle this terminal addition, then this says like you're good to go. Okay. I don't see any questions, so I will move forward. So now there's this, obviously we're working with a subclass of linear systems, and Laplacians are tightly connected to graphs. There is this correspondence between Laplacians and graphs, and usually we've seen a lot of transfer between like combinatorial techniques and continuous optimization. Now here, I think we're taking a step in the other direction. So we take this algebraic object, this short complement, which you can get by blood-loss elimination. And what we do is we view it as a combinatorial thing. Okay, so what is the interpretation? So at a high level, you can think of, I can write this process of eliminating vertices as a bunch of random walks on graphs. Okay, and ideally, this is nice because we know somewhat random walks are local, and then we can exploit this somehow, and you will see that we'll be able to do that with some work. Okay. So now here's one point. These are all dense objects. First, we need some sparse representation of it. So we do the sparse representation in two steps. The first step is as follows. We do this very simple minded process. We start as follows. So you get an edge in the graph. You take the endpoints of this edge, and then you do a random walk until you hit a red vertex. from one endpoint. So then you do another random walk from the other point until you hit a vertex. And then you concatenate these walks, you reweight it, and you add it to the Sparsifier as a single edge. But now the endpoints of this walk are going to be the terminals, okay? And so then you repeat this for every edge. You take another edge, you take one endpoint, you do a random walk until you hit the terminal. You do another random walk until you hit the terminal, then you add this edge. Okay, so you keep doing this for, so this factor that you see there, 1/epsilon², again, these are just things that come from matrix Chernow bonds, right? You just want to prove high concentration of these things. So this is fairly additive. We're just doing it, we're just adding a bunch of random walks together, right? And you can show that, in fact, in expectation, this is good. And so in expectation, I preserve the short complement with this procedure. So now let me get into the business of sparsity. I'm doing this for m edges. So I'm going to have at least m edges here, right? But I can sparsify. So this is a graph on m edges, but has fewer vertices. I'm just going to run Spectral Sparsifier on this. And then I will make it proportional to the number of vertices. Okay? And the claim is that age is an approximation to the short complement with high probability. So we also get concentration, and concentration will just use some matrix Chernow bond. By now, these things are standard. Maybe they were not that standard 15 years ago. Now we know how to use them in this context. Okay, so this is the first step. So are we done? The question is, how fast can I hit a red vertex, right? Because cover time in graph can be very large, right? So we're not yet done. And this is not that efficient, right? So we need another thing, and probably some of you that have worked with graph algorithms have guessed it already. And this is just like doing randomization or throwing some darts in your network. And the main purpose here is just to make sure that these random walks are short. Okay, so I will carefully pick some vertices in my network or graph, some random subset of vertices, and I will add them to the terminal set. I will append the terminal set with this sublinear number of vertices, and then I will make sure that these walks are short. Okay, and by short I mean something sublinear in the size of the network. And now we are in a good position. Why? Because first, how efficiently can I generate a random walk in a graph? Well, you can do this proportional to the length of the walk, but the walks are short now, right? So, and I had roughly n random walks, because for each edge I had a random walk. And then these are short, so the time to construct this graph H now is going to be n to the 3/2. Just by multiplying the length of the walks, the worst case length of the walk with the number of walks you're doing. And then actually for adding a terminal, this is very intricate, and we are using heavily amortization here. And what we are making sure here is that whenever you add a terminal, whenever you see these black vertices, whenever you decide to make a black vertex a red vertex in the graph, these walks are just becoming shorter and shorter, right? Because eventually, if you add every vertex to be, if you declare every vertex to be a red vertex, you just get the original graph, right? So these walks are becoming shorter and shorter, and then we can charge this to construction time. So we maintain some data structures to maintain these walks proportional to the time it took them to generate them in the first place. And we heavily use amortization. In this case, adding a terminal will essentially be for free, up to polylog factors. Okay, so now I will briefly tell you why we care about this. I'm not going to define max flow again. I'm pretty sure everybody knows here. So I'll skip it. And so as you saw in Richard's talk yesterday and in Jan's talk today, all of these things have been very useful in term-point methods. And how can you use dynamic data structure in term-point methods, especially dynamic Laplacian solvers? Well, they appear especially if you define some sort of flow problem or variant of flow problem. And two variants that people have looked in the literature mainly are maximum flow problem and the mean cost flow problem. And when you do interior points, it seems that the sequence of these linear systems you need to solve in each iterations are Laplacian systems. And then that's where you use these data structures that I just described to get better running times per iteration. Instead of computing a Laplacian system from scratch, you use the data structure to make them more efficient. And this was used very recently before this breakthrough Maxwell paper came up. This was used for getting the first m to the 3 over 2 minus some constant bound for breaking this m to the 3 over 2 Goldberg-Rao standard result that has been there for many years. And it has been an extended to max mean cost flow, and they are using this dynamic Laplacian solver that I just described. And so again, if you care by planar graph for planar graphs, then you can actually get near linear time. And essentially, that's near linear time algorithm is using essentially that algorithm I just told you in a slide where you can maintain this approximation complements in planar graphs. Using this hierarchy of short complements and order divisions and nested dissection. And for this, actually, we know now that this is essentially tight, while the Maxwell result still pays a subpolynomial effect in the running time. So for planar graphs, we actually close the problem using the same technique, so using dynamic Laplacian solvers. Okay, so the second part of the talk, this is going to be much briefer. But I will try to convey some intuition, probably won't get into the details and everything. And I want to tell you about vertex sparsification for cuts now. You heard about this L2 distances or effective resistances. Now I want to tell you about cuts and how to use actually some techniques to get vertex sparsification for cuts. And why do we care about this? Well, so one of my favorite problems is a fully dynamic max flow. It seems that we are far away from understanding this problem, and we've done some work on this. Essentially, we get the arguably high approximation guarantees. We do get sublinear times, but obviously we'd like to see some 1 plus epsilon there. But these are the first works towards that goal. And we know what exact can be done. And there were some prior works, but they looked at special cases, like special family of graphs or bounded connectivity. So, and now I want to tell you that this vertex sparsification also applies to dynamic max flow. Okay, so here is one useful notion, and probably this has been formalized before, but at least I got to learn about this by this work of Ankul Moitra in 2009, and he introduced this notion of cut preserving vertex Sparsifiers. And before I tell you what this is, let's just look at the simple notion of what a terminal cut is. So again, I'm giving this graph, these vertices, some of them are labeled black, some of them are labeled red. And I would like to find what is the minimum terminal cut. So what is, so you can, as you see, you have many bipartitions in the graph that cut the terminal set. And the minimum terminal cut is the one that achieves this minimum, right? And you know, the way to cut is just the number of edges going across the cut. And what this definition of Moitra says is that what is especially a cut Sparsifier for graphs is essentially, I give you a graph and I would like to have a smaller graph with this. I think Moitra had this setting where the terminals, so the terminal set of the Sparsifier needs to be only the terminal, so you don't allow any Steiner vertex. But you could expand that. And you would like to preserve essentially all these terminal cuts up to an alpha factor, and this Sparsifier has to be very small. So think of this like this would have billions of nodes and three nodes as terminals, and I would like just a graph on 3 nodes, but still capturing the cut structure of the graph, right? So it's very strong in that sense. And this has been used a lot in approximation algorithms. And here I would like to tell you one way of doing cut sparsification, which I think is an overkill, but it's easy. So now let's look at this notion of tree approximations. So what is a tree approximation? I give you a graph. I would like to construct a single tree that captures the cut flow of the graph. And well, we know for this you have to pay at least a log, like a log in the quality. You can go beyond that. And this has been studied, and I think this work has been initiated by Reke. And So essentially, the main observation is that you can get, nowadays you can get such cut Sparsifiers or tree cut Sparsifiers. You pay some polylog and guarantee on the side, on the quality, and then you can construct them in near linear time. So how do you get cut Sparsifiers? So this is the last thing I'm going to tell you, and then I'm going to stop. So how do you get vertex Sparsifier from tree Sparsifiers? I think this is useful, so maybe you just do this, okay? So you first, you take the graph, you construct the tree cut Sparsifier. Now, this might have some additional Steiner vertices. These are labeled blue, but there is one-to-one correspondence between leaves of the tree and the vertices of the underlying, okay? And if this tree is shallow, and by shallow I mean it has log depth, then you just take this leaf to root paths. And this will give you Sparsifiers like k times some polylog depth. Okay. If the tree is not shallow, then you can do rate compress. So you can get rid of degree 2 vertices and or like degree 1, and then you can show that the graph ends up with at most 2k vertices, where k is the number of terminals. Okay, so unfortunately, I don't have time to go through everything I plan to. But Fachapol will talk about we have a new construction on tree cut Sparsifier, and Fachapol will talk more about this in his talk. And then, yeah, I'll also skip this one. So here are a few things that I didn't talk about, I didn't have time to talk about in this talk, and that they are interesting, so you might find it useful if you want to further explore this space of vertex Sparsification and how it connects to dynamic and other areas in algorithm design. And yeah, I will just conclude here, stop here, and I'm happy to take questions. Thanks very much for listening. Yeah. You just, yeah, so you start with a terminal set of size, say, square root of m, and then you wait for square root of m terminal additions, and then you recompute from scratch, and you can amortize that to the preprocessing time, given your preprocessing time is not huge, right? It does require efficient preprocessing time. And so it's the trivial thing you do, right? Yeah. Nothing. Okay. Thanks again. PowerPoint.